Earth did not begin as a world of forests, oceans, and animals. It began as a violent experiment. A molten sphere orbiting a young, unstable sun, bombarded by asteroids, torn from the leftovers of planetary formation. For hundreds of millions of years, there was no life, no soil, no oxygen, rich air, only fire, rock, and chaos. Yet within this hostile environment, the foundations of every future extinction were already being set. To understand mass extinctions, we must first understand that Earth is not a stable planet. It is a system constantly changing, driven by forces far larger than life itself. Tectonic plates move, continents collide, and separate oceans open and close. Volcanoes reshape the atmosphere. The sun slowly brightens over time. Even the chemistry of the air and oceans is not fixed. Life does not control these systems. Life adapts to them until it no longer can. The earliest Earth was defined by extremes. Temperatures were high, the surface was unstable, and impacts were frequent. Water arrived from icy asteroids and comets, forming the first oceans. Within those oceans, chemistry began to organize itself. Simple molecules bonded formed chains, and eventually became self-replicating systems. Life emerged quietly, not as animals or plants, but as microscopic organisms, invisible yet powerful. For billions of years, Earth belonged entirely to microbes. They ruled the oceans, the atmosphere, and the surface chemistry of the planet. Some of them changed the world forever. Cyanobacteria learned to use sunlight to produce energy, releasing oxygen as waste. At first, oxygen was toxic to most life. It reacted with iron-poisoned cells and altered ocean chemistry. This event, now known as the Great Oxygenation, fundamentally transformed Earth. This was not a mass extinction in the traditional sense, but it was the first planetary-scale biological crisis. Countless anaerobic organisms died as oxygen levels rose. The atmosphere changed from a reducing state to an oxidizing one. The sky itself may have shifted color. Earth-cooled glaciers formed, and life was forced to adapt or disappear. Extinction was already part of the system long before animals existed. This early transformation reveals a critical truth. Extinctions are not accidents. They are consequences of imbalance. When Earth systems change faster than life can adapt, collapse follows. Sometimes the trigger is internal, such as oxygen buildup or volcanic activity. Sometimes it is external, such as asteroid impacts. But the outcome is always the same. Ecosystems unravel. As life diversified, complexity increased, but so did vulnerability. Simple organisms can survive extreme conditions. Complex ecosystems cannot. They depend on stable food webs, predictable climates, and narrow environmental ranges. The moment those conditions shift too far, too fast, extinction becomes inevitable. Earth's 5 mass extinctions are not random disasters scattered through time. They are connected chapters in a long planetary narrative. Each one follows a familiar pattern. Environmental stress accumulates, thresholds are crossed, and collapse accelerates. Once a critical tipping point is reached, recovery becomes impossible within existing ecosystems. Before the first recognized mass extinction, the planet appeared stable on the surface. Oceans were rich with life, reefs flourished, and biodiversity was high. Yet beneath that apparent stability, Earth systems were already drifting. Climate cycles intensified, sea levels fluctuated, and chemistry shifted. Mass extinctions often begin long before the final collapse becomes visible. This is one of the most dangerous illusions in Earth history. Stability can hide fragility. Ecosystems can appear healthy even as the forces that sustain them weaken. By the time extinction becomes obvious, it is usually too late to reverse. Mass extinctions are defined not by the disappearance of all life, but by speed and scale. They represent moments when extinction rates increase dramatically across many unrelated groups in a geologically short period of time. They wipe out dominant species, erase entire ecosystems, and reset the evolutionary trajectory of the planet. Yet, extinctions are not the end of life. They are transitions. Every mass extinction clears ecological space. Niches, open resources become available, and survivors expand in new directions. Without extinction, there would be no dinosaurs. Without later extinction, there would be no mammals. Life advances through loss. But this does not make mass extinctions neutral or harmless. Each one represents unimaginable biological suffering. Species that took millions of years to evolve vanish permanently. Evolutionary experiments end. Entire branches of the tree of life are cut away. Recovery takes millions of years, not centuries. Earth's history shows that recovery is never a return to what was lost. Post-extinction worlds are fundamentally different. New dominant groups emerge, climates stabilize at new baselines, and ecosystems reorganize from the ground up. Extinction is a reset, not a rewind. The 5 mass extinctions did not happen because life failed. They happened because Earth changed. The planet does not prioritize biodiversity or stability. It follows physics, chemistry, and orbital mechanics. Life exists at the mercy of these forces. This is why mass extinctions are not evenly spaced through time. They cluster around periods of extreme planetary change. Supercontinent formation, massive volcanism, rapid climate shifts, and extraterrestrial impacts all coincide with biological collapse. Understanding mass extinctions requires abandoning the idea that Earth is a nurturing, balanced system. It is not designed for life. Life is an outcome, not a goal. The same processes that allow life to flourish can just as easily destroy it. This chapter is not about death alone. It is about context. Before we examine each extinction, we must understand the stage on which they occur. Earth is a dynamic machine, constantly adjusting energy flows, material cycles, and surface conditions. Life is a participant, not a controller. The illusion of permanence is one of the greatest misconceptions in natural history. Species feel permanent while they exist. Ecosystems feel ancient while they function. But in geological time, even the most successful life forms are temporary. Humans often view extinction as failure or tragedy. In Earth history, extinction is expected. The planet has erased dominant life forms repeatedly. What matters is not whether extinction happens, but how fast and how complete it becomes. The 5 mass extinctions represent moments when Earth crossed thresholds too extreme for existing life to survive. They are warnings written into stone, fossil, and isotope ratios. They tell a story of limits. As this documentary unfolds, we will move through deep time, exploring each extinction in detail. We will examine what triggered them, how life collapsed, and how the planet recovered. But all of them begin here with a simple truth. Earth is alive with change, and change does not ask permission. This is the foundation of extinction. Long before the first mass extinction erased complex ecosystems, Earth was already a world shaped by disappearance. Extinction did not begin with animals. It began with chemistry. The earliest life forms were fragile molecular systems surviving in narrow conditions. Even slight environmental shifts could end entire lineages without leaving fossils or traces. Extinction was silent but constant. For nearly 3 billion years, life existed almost exclusively as single-celled organisms. Bacteria and archaea dominated every environment, from shallow seas to deep hydrothermal vents. These organisms were resilient, but not invincible. Changes in temperature, ocean chemistry, salinity, or radiation could wipe out entire microbial communities. The difference was scale. Extinction happened slowly and locally, not globally. This long microbial age created the illusion of permanence. Life persisted, but innovation was rare. Complexity was limited by energy availability and environmental stability. The planet itself was still settling into long-term patterns. Tectonic plates were smaller and more active, volcanoes were frequent, and impacts still occurred regularly. Stability was relative, not absolute. The atmosphere during this time was fundamentally different from today. Oxygen was scarce. Methane, carbon dioxide, and nitrogen dominated the air. Ultraviolet radiation from the young sun reached the surface largely unfiltered. Life survived underwater or beneath sediment, where radiation exposure was reduced. Land was a barren, toxic landscape. The first true planetary crisis came with oxygen. When photosynthetic microbes began releasing oxygen, they unintentionally destabilized the entire biosphere. Oxygen reacted with methane, a powerful greenhouse gas causing global cooling. Ice ages spread across the planet, possibly freezing oceans nearly to the equator. This event may have nearly ended life entirely. Again, this was not one of the 5 recognized mass extinctions because animal life had not yet emerged. But it established a pattern that would repeat. A biological innovation altered the environment, triggering climate collapse and widespread extinction. Life changed the planet, and the planet pushed back. After oxygen stabilized, complex cells emerged. Eukaryotes developed internal structures, allowing greater efficiency and size. Eventually, multicellular life appeared. Cells specialized, coordinated, and formed organisms capable of movement, predation, and sensory perception. Life crossed a threshold of complexity. With complexity came dependency. Multicellular organisms relied on stable oxygen levels, predictable temperatures, and reliable food sources. They evolved slowly relative to environmental change. This made them vulnerable in ways microbes never were. The oceans became laboratories of experimentation. Strange body plans emerged, many of which would later disappear entirely. Early animals explored symmetry, mobility, and feeding strategies. Ecosystems formed layered food webs with producers, consumers, and decomposers. For the first time, extinction could cascade. The Cambrian period represents both an explosion of life and a warning. Diversity increased rapidly, but so did competition. Predators evolved hard shells, eyes, and weapons. Prey evolved armor, speed, and burrowing behaviors. Ecosystems became dynamic but fragile. This early complexity masked underlying instability. Ocean chemistry fluctuated, oxygen levels varied between regions, and climates shifted. Even during times of apparent abundance, many lineages were living close to environmental limits. Extinction events occurred repeatedly throughout this early era, but they were smaller and more regional. Shallow seas could lose entire communities due to anoxic events where oxygen disappeared from the water. Temperature spikes could eliminate species adapted to narrow ranges. Reefs collapsed and reformed multiple times. These early extinctions refined ecosystems. Inefficient body plans vanished. Survivors adapted to broader conditions. Life learned resilience through repeated loss. But resilience has limits. As continents shifted, shallow seas expanded and contracted. Sea level changes repeatedly destroyed habitats. Most early animal life lived in shallow marine environments, making them especially vulnerable to fluctuations. A small change in sea level could erase entire ecosystem. This vulnerability set the stage for the first true mass extinction. By the late Ordovician period, biodiversity was high but concentrated. Most species occupied similar environments, relied on similar conditions, and shared similar physiological limits. The system was diverse, but not robust. This pattern would repeat throughout Earth history. High biodiversity does not guarantee stability. In some cases, it increases risk. When many species depend on the same environmental conditions, a single disruption can trigger widespread collapse. Another critical factor was time. Evolutionary innovation lags behind environmental change. When blink in geological time, but devastating for ecosystems. Life before the first mass extinction existed in a world without precedent. Ecosystems had never faced global-scale disruption. There were no evolutionary templates for survival under extreme conditions. Specialization had increased, but flexibility had not. This is a critical concept. Evolution optimizes for current conditions, not future threats. Species that thrive during stable periods are often the most vulnerable when conditions change. Success creates fragility. By the end of the early Paleozoic, Earth had reached a tipping point. Climate oscillations intensified, polar ice expanded, sea levels dropped, and shallow marine habitats vanished. What followed would mark the first moment when extinction became truly global. But that collapse did not come without warning. Chemical signatures in rocks show stress long before the final extinction pulse. Oxygen levels fluctuated, isotopes shifted, and biodiversity began to decline unevenly. Extinction often begins quietly. This chapter reveals that mass extinctions are not sudden accidents. They are the culmination of long processes. The planet accumulates stress until systems fail. Before the first mass extinction, life had already experienced loss, adaptation, and recovery many times. But nothing had tested the biosphere at a planetary scale. Nothing had removed most life across multiple environments simultaneously. That threshold was about to be crossed. The story of mass extinction begins not with catastrophe, but with imbalance. It begins when Earth systems drift beyond what life has learned to endure. In the next chapter, the planet will enter that threshold for the first time. By the time the Ordovician period began, Earth had transformed into a water-dominated world rich with life. Continents were clustered mostly in the southern hemisphere, and vast, shallow seas flooded continental margins. These warm sunlit waters became biological engines, producing an explosion of diversity unlike anything seen before. For the first time, complex ecosystems spread across the planet on a truly global scale. The Ordovician oceans were crowded. Trilobites thrived in countless forms, occupying nearly every marine niche. Brachiopods carpeted the seafloor, filtering nutrients from the water. Early corals built reef-like structures that stabilized ecosystems and created shelter for smaller organisms. Cephalopods emerged as dominant predators. their straight shells acting as buoyant weapons drifting through open water. Life was still almost entirely marine. Land remained largely barren, with no plants, no soil, and no animal ecosystems. Rivers carried minerals into the oceans, fueling productivity. Photosynthetic algae bloomed, feeding complex food webs. Oxygen levels rose further, allowing larger bodies and higher metabolic rates. This apparent prosperity concealed a dangerous concentration of risk. Most life depended on shallow marine environments. Temperature, salinity, and oxygen levels needed to remain within narrow ranges. Unlike deep ocean ecosystems, which are buffered from surface change, shallow seas respond rapidly to climate shifts. During the early Ordovician, climate was warm and relatively stable. Sea levels were high, flooding continental shelves. Habitats expanded and species radiated rapidly. Biodiversity climbed to levels not seen again for hundreds of millions of years. Yet high diversity did not equal resilience. As the period progressed, Earth began to cool. The cause was not a single event, but a convergence of slow planetary processes. Continental drift moved large landmasses toward the South Pole. Weathering of exposed rock drew carbon dioxide from the atmosphere, reducing greenhouse warming. Ocean circulation patterns shifted, redistributing heat unevenly. Glaciers began forming on the southern supercontinent. At first they were limited, but their growth marked a fundamental change. Ice reflects sunlight, amplifying cooling. As temperatures dropped, glaciers expanded, accelerating the process. This feedback loop would prove devastating. Cooling climates alone do not cause mass extinctions. Life has survived ice ages before. The true danger lay in how cooling altered sea levels. As water became locked in ice, global sea levels fell dramatically. Shallow seas drained, exposing vast areas of seafloor. For organisms adapted to narrow depth ranges, this was catastrophic. Habitats disappeared faster than species could migrate or adapt. Reef systems collapsed. Filter feeders lost stable environments. Predators lost prey. Extinction cascaded through the food web. The first phase of the Ordovician extinction struck cold. Adapted species survived temporarily, while warm water species vanished. Extinction was selective at first, targeting those unable to tolerate temperature change. But the system continued to destabilize. Oxygen levels in the oceans dropped as circulation slowed. Cold water holds more oxygen, but stratification increased, creating anoxic zones. Organisms trapped between cold, oxygen-rich surface waters and oxygen-poor depths faced lethal conditions. The extinction unfolded in waves. Initial cooling eliminated tropical species. Sea level fall destroyed habitats. Anoxia finished what climate began. By the peak of the crisis, roughly 85% of marine species had vanished. This was Earth's first true mass extinction. It was global, rapid, and severe. Entire ecological structures disappeared. Dominant groups that had flourished for millions of years were reduced to remnants or erased entirely. Yet the planet did not remain frozen. After reaching a maximum, glaciers began to retreat. Volcanic activity increased, injecting carbon dioxide back into the atmosphere. Temperatures rose rapidly, reversing the cooling trend. This sudden warming created a second extinction pulse. Species that had adapted to cold conditions were now exposed to heat stress. Oxygen levels shifted again. The instability proved deadly to survivors already weakened by the first collapse. This two-phase nature makes the Ordovician extinction particularly destructive. It was not a single disaster, but a rapid oscillation between extremes. Life was trapped between incompatible conditions, unable to stabilize. The fossil record shows stark boundaries. Diverse assemblages vanish, abruptly replaced by impoverished communities dominated by a few hardy survivors. Complexity collapsed. Ecosystems simplified drastically. Yet, even in devastation, some lineages endured. Small generalist species with broad tolerances survived. Organisms capable of living in deeper waters or migrating vertically fared better. Flexibility determined survival. This pattern would repeat in later mass extinctions. Specialists dominate during stable periods, but generalists survive chaos. Ecological success becomes evolutionary weakness. The Ordovician extinction reshaped marine life permanently. When recovery began, the survivors diversified into new forms, filling vacant niches. Reefs eventually returned, but built by different organisms. Food webs reorganized from the bottom up. This extinction also established a precedent. It proved that climate change alone, without impacts or massive volcanism, could destroy global ecosystems. Gradual processes accumulated until thresholds were crossed and collapse followed swiftly. Perhaps most importantly, it demonstrated that Earth systems can shift faster than life can adapt. Geological change does not need to be sudden to be lethal. Sustained imbalance is enough. The Ordovician world reminds us that extinction does not require violence. No asteroid struck, no supervolcano erupted. The planet simply cooled, and that was enough. In the next chapter, we will examine how life attempted to recover from this first great collapse and how that recovery sowed the seeds for future catastrophes. When the ice retreated and sea levels slowly rose again, the planet emerged from its first mass extinction, altered and unstable. The Ordovician-Silurian boundary marks not just a moment of loss, but the beginning of Earth's first great recovery experiment. Life returned to emptied seas, but it did so cautiously, unevenly, and under conditions that were far from stable. The aftermath of extinction is never a clean slate. Survivors inherit a damaged world. Ocean chemistry remains disrupted. Climates fluctuate, and ecosystems lack the complexity that once buffered them against change. Recovery is slow because the conditions that caused extinction often persist long after the worst losses occur. In the early Silurian period, warming resumed. Glaciers melted, releasing fresh water into the oceans. Sea levels rose, flooding continental shelves once again. New, shallow marine habitats formed, creating opportunity for recolonization, but the oceans were chemically altered. Oxygen levels varied dramatically from place to place, and anoxic zones lingered in deeper waters. The species that survived the Ordovician extinction were not the most impressive or dominant of their time. They were the adaptable, the small, the generalists. These organisms became the founders of new ecosystems. Evolution after extinction is driven less by innovation and more by expansion. Survivors spread into empty niches and diversify rapidly. Reef systems slowly reappeared, but they were simpler and more fragile than before. The organisms that once built massive, complex structures were gone. New reef builders lacked the same efficiency and resilience. Early Silurian reefs were unstable, frequently collapsing under environmental stress. Predator-prey relationships had to be rebuilt. With many predators extinct, prey populations initially exploded only to crash when food sources were exhausted. Ecosystems oscillated wildly, lacking the regulatory balance that develops only after long periods of stability. This instability is a defining feature of post-extinction worlds. Biodiversity increases, but volatility remains high. Small changes in temperature, sea level, or chemistry can still trigger local collapses. Recovery does not mean safety. The Silurian seas eventually stabilized enough to support diversification. Jawed fish emerged, marking a significant evolutionary leap. These new predators introduced mobility, speed, and active hunting into ecosystems. Armor and defensive adaptations followed as evolutionary arms races resumed. Yet, beneath this apparent progress, Earth systems continued to drift. Continental positions changed, ocean currents reorganized, and greenhouse gas levels fluctuated. The planet had entered a pattern of long-term instability. The lesson of the first mass extinction was not fully learned. Life rebounded, but it rebuilt itself atop shifting ground. Resilience improved, but vulnerability remained. On land, a quiet revolution began. Simple plants started colonizing coastal environments. These early terrestrial pioneers lacked roots and leaves as we know them, but they began altering the atmosphere and soil chemistry. They stabilized sediments, reduced erosion, and drew carbon dioxide from the air. This greening of the land would eventually transform Earth, but in the short term, it introduced new feedbacks. Increased weathering, altered ocean nutrient flows, carbon cycles shifted again, influencing climate patterns. Mass extinctions often leave hidden legacies. The recovery itself changes the planet, setting up conditions for future crises. Life is not merely responding to Earth, it is reshaping it. By the late Silurian, biodiversity approached pre-extinction levels in some regions. But the composition of life was different. Entire groups lost during the Ordovician never returned. New lineages took their place, creating ecosystems with unfamiliar structures and dynamics. This pattern is universal across mass extinctions. Recovery restores numbers, not identities. The biosphere moves forward, not backward. The success of the Silurian recovery created another illusion of permanence. Reefs expanded, fish diversified, and food webs grew complex once more. From a human perspective, the planet appeared healed. But geological records reveal continued stress beneath the surface. Oxygen levels fluctuated dramatically during this time. Some regions experienced hypoxic events, where oxygen dropped suddenly, killing marine life. These were warning signals of instability that foreshadowed larger collapse. The rise of plants on land also increased nutrient runoff into the oceans. Excess nutrients fueled algal blooms, which upon decay consumed oxygen, creating dead zones. Ecosystems thrived and suffocated at the same time. This dynamic would later play a central role in future mass extinctions. The interaction between life and environment can amplify stress rather than reduce it. By the early Devonian period, Earth was again a planet of opportunity. Ecosystems were expanding into new realms. Fish ventured into freshwater systems. Plants spread inland, forming the first primitive forests. Soils developed and rivers changed course. But expansion carries cost. As life spreads, it becomes more interconnected. Disturbances propagate farther and faster. Resilience requires redundancy, but early complex ecosystems lacked that depth. The first mass extinction taught life how to recover, but it did not eliminate the forces that caused extinction. Climate instability, sea level fluctuation, and ocean anoxia continued to shape the planet. In geological time, recovery and collapse are not separate phases. They overlap. While some regions heal, others destabilize. Extinction is not a single moment, but a process with long shadows. The Ordovician Silurian extinction established a template that would repeat 4 more times: slow environmental drift, sudden threshold crossing, rapid collapse, and prolonged recovery. Each extinction would differ in cause and scale, but the structure remains consistent. This chapter underscores a critical truth. Extinction does not end when the dying stops. Its consequences unfold for tens of millions of years, shaping evolution long after the crisis has passed. Life survived its first global catastrophe. It adapted, diversified, and expanded into new forms. But the planet it inhabited was now more complex, more interconnected, and more vulnerable. The stage was set for the next great test. In the following chapter, the world will enter the Devonian age, a time of innovation, abundance, and hidden instability that would lead to Earth's second mass extinction. The Devonian period opened with promise. Life was no longer confined to the oceans alone. The planet was entering an age of expansion, where ecosystems grew more complex, more connected, and more ambitious than ever before. What followed looked like progress. But beneath that progress, the foundations of instability were quietly forming. The seas of the early Devonian were dominated by fish. Jawless fish that had survived earlier. Upheavals now shared the water with newly evolved jawed species. These animals were faster, stronger, and more efficient predators. Armor thickened, fins diversified, and mobility improved. The oceans became arenas of constant evolutionary pressure. Reef systems flourished again. They spread across shallow tropical seas, forming massive biological structures that rivaled modern coral reefs in scale. These reefs supported dense communities of invertebrates, fish, and microorganisms. Productivity soared and biodiversity climbed. On land, a revolution was underway. Plants had moved beyond coastal margins. They developed vascular systems, allowing them to transport water and nutrients internally. Roots anchored them into soil, extracting minerals and stabilizing landscapes. The first true forests began to appear. This transformation of land was one of the most profound events in Earth history. Forests changed everything. They altered weathering rates, drew carbon dioxide from the atmosphere, and released oxygen. Soils deepened, rivers slowed, and sediments shifted. Land itself became a living system. Animals followed plants onto land. Early arthropods crawled across forest floors, feeding on decaying matter. Ecosystems expanded vertically with canopies, shade, and complex microhabitats. Earth was becoming three-dimensional. From a biological perspective, the Devonian was an age of success. Life was spreading, diversifying, and reshaping the planet. Yet this success carried hidden risks. Ecosystems were becoming increasingly interconnected. Changes in one system now affected many others. The expansion of forests dramatically increased nutrient runoff into rivers and oceans. Roots broke down rock, accelerating chemical weathering. Phosphorus and other nutrients washed into seas, fueling algal growth. Productivity increased, but so did instability. Algal blooms consume oxygen when they decay. In coastal and shallow marine environments, this created anoxic conditions lethal to many organisms. Dead zones began appearing sporadically. Reefs, sensitive to oxygen fluctuations, suffered repeated stress. These were not isolated events. Geological records show widespread oxygen depletion in Devonian oceans. Entire regions experienced prolonged anoxia. Black shale deposits formed as organic matter accumulated without decay. Life thrived and suffocated simultaneously. climate also became unstable. While forests removed carbon dioxide, cooling the planet, volcanic activity periodically injected greenhouse gases, warming it again. Temperatures oscillated, placing stress on organisms adapted to narrow ranges. The Devonian extinction did not arrive as a single catastrophe. It unfolded over millions of years through a series of pulses. This makes it less dramatic in popular imagination, but no less devastating in outcome. Species disappeared in waves. Reef builders declined repeatedly, failing to fully recover between events. Fish diversity dropped, especially among armored placoderms that had dominated earlier seas. Ecosystems weakened incrementally. This slow erosion of biodiversity is particularly dangerous. Unlike sudden extinctions, it does not immediately clear niches. Instead, it destabilizes food webs, leaving systems fragile and prone to collapse. One of the most significant losses occurred among reef ecosystems. Once destroyed, they failed to return to previous complexity for tens of millions of years. This left shallow marine environments vulnerable to further stress. The causes of the Devonian extinction are complex and still debated. What is clear is that it was driven by internal planetary feedbacks rather than a single external trigger. Life itself played a central role. The greening of the land altered atmospheric composition, climate, and ocean chemistry. In doing so, it pushed Earth systems beyond stable ranges. This is a recurring theme in mass extinctions. Biological success can destabilize the environment that supports it. Another contributing factor may have been ocean circulation changes. Continental positions altered current patterns, reducing oxygen delivery to deep waters. Stratified oceans trap nutrients and limit mixing, creating ideal conditions for anoxia. By the late Devonian extinction rates spiked sharply. Entire groups vanished. The once dominant placoderm fish disappeared entirely. Trilobites, which had survived earlier extinctions, were reduced to shadows of their former diversity. Yet, unlike the Permian extinction that would follow later, the Devonian did not annihilate ecosystems completely. It selectively targeted certain environments and groups. Freshwater systems and terrestrial ecosystems were less affected. This uneven impact reshaped the direction of evolution. Survivors inherited a world with fewer competitors and altered ecosystems. Fish lineages that would later give rise to tetrapods gained prominence. Early vertebrates ventured closer to land. In this way, extinction acted as a filter. It removed dominant groups and allowed marginal ones to expand. Evolutionary trajectories shifted permanently. The Devonian extinction teaches an important lesson. Mass extinction does not always come as a single dramatic event. It can be slow, cumulative, and deceptive. Ecosystems can appear productive even as they unravel internally. This kind of extinction is particularly difficult to recognize in real time. By the time biodiversity loss becomes obvious, the underlying causes may have been active for millions of years. Earth emerged from the Devonian altered but not destroyed. Forests persisted, land ecosystems continued expanding, and new marine communities formed. Life adapted once again. But the planet had entered a dangerous phase. Biological and geological systems were now tightly coupled. Changes in one amplified changes in the other. Feedback loops grew stronger. This coupling increased the stakes. Future disturbances would propagate faster and farther. Resilience would require greater adaptability. The Devonian extinction set the stage for the most catastrophic collapse in Earth history. By reducing ecological diversity, and increasing specialization, it made the biosphere vulnerable to extreme stress. The planet had survived 2 mass extinctions. Each time, life rebounded more complex and more interconnected than before. Each time, the margin for error narrowed. What followed would push Earth beyond any previous limit. In the next chapter, the world will approach the brink during the Permian period, when Earth nearly lost everything. The Permian period began quietly, but uneasily. On the surface, life appeared to be thriving again. Forests spread across vast interiors, continents stabilized, and animal lineages diversified into forms that would later dominate the planet. Yet, this apparent stability masks the most dangerous configuration Earth had ever assembled. For the first time in its history, nearly all landmasses merged into a single supercontinent. Pangea stretched from pole to pole, creating a world defined by extremes. Coastlines shrank, interiors expanded, and oceans were pushed outward into a single vast basin. This rearrangement altered every major Earth system at once. Pangea changed climate fundamentally. With so much land far from the moderating influence of oceans, temperatures became extreme. Summers grew brutally hot, winters severe and dry. Rainfall patterns collapsed in continental interiors, creating immense deserts. Seasonal swings intensified, stressing ecosystems adapted to narrower ranges. Coastal regions remained productive, but they were limited in area. Shallow seas, which had supported most marine biodiversity throughout Earth history, were reduced dramatically. Habitats contracted while competition increased. This alone would have been enough to strain life. But Pangea also disrupted ocean circulation. With fewer seaways connecting oceans, currents slowed and deep waters became stagnant. Oxygen delivery to the depths declined, setting the stage for widespread anoxia. Marine ecosystems depend on circulation. When it fails, oxygen drops, nutrients accumulate, and toxic conditions emerge. The Permian oceans were drifting towards suffocation. On land, forests, adapted to dry climates, expanded. Early conifers, seed ferns, and other drought-tolerant plants dominated. They supported new herbivores and predators among reptiles and synapsids. These animals developed advanced features, including improved lungs, temperature regulation, and more efficient movement. The ancestors of mammals thrived during this time. Large predators and herbivores occupied roles that would later be filled by dinosaurs. Ecosystems were complex, structured, and highly specialized. Specialization, however, is a double-edged trait. It increases efficiency under stable conditions, but reduces adaptability under change. Permian life was optimized for a world that would soon disappear. Beneath the surface, Earth's interior was becoming increasingly active. Massive mantle plumes rose toward the crust beneath what is now Siberia. Pressure built over millions of years, preparing for one of the largest volcanic events in planetary history. When it began, it did not explode once and end. It unfolded in phases, releasing unimaginable volumes of lava, gas, and ash over hundreds of thousands of years. The Siberian traps covered millions of square kilometers, flooding landscapes repeatedly. Volcanism of this scale transforms the atmosphere. Carbon dioxide poured into the air, driving rapid warming. Sulfur dioxide formed aerosols, initially cooling the planet, then falling as acid rain. Methane was released from sediments, amplifying greenhouse effects further. The climate swung violently. Temperatures rose far beyond levels most life could tolerate. Tropical oceans warmed, reducing oxygen solubility. Warm water holds less oxygen accelerating anoxia. Dead zones expanded globally. As oceans lost oxygen, anaerobic bacteria flourished, producing hydrogen sulfide, a toxic gas lethal to most complex life. Evidence suggests this gas may have escaped into the atmosphere, poisoning coastal and terrestrial ecosystems. This was not a sudden apocalypse. It was a slow, tightening noose. Ecosystems weakened gradually, then collapsed rapidly once thresholds were crossed. Coral-like reef systems, which had never fully recovered from earlier extinctions, vanished entirely. They would not return in recognizable form for tens of millions of years. Marine food webs disintegrated from the base upward. On land, heat stress, drought, and acid rain devastated forests. Soils eroded, vegetation collapsed, and food chains broke. Herbivores starved, predators followed. Extinction cascaded through terrestrial ecosystems. By the peak of the crisis, roughly 90% of marine species and 70% of terrestrial vertebrates disappeared. This was Earth's greatest extinction event, the Great Dying. Entire evolutionary lineages ended permanently. Trilobites, which had survived multiple extinctions, vanished forever. Dominant predators disappeared. Ecosystems simplified to a few hardy survivors. The planet itself entered a near-death state. Recovery did not begin immediately. For millions of years, biodiversity remained extremely low. Microbial communities dominated landscapes, oceans remained hostile, and complex life struggled to re-establish. The Permian extinction represents a critical boundary in Earth history. It demonstrates that there are limits beyond which recovery becomes extraordinarily slow. When extinction removes too much complexity, the biosphere loses its capacity to rebound quickly. This event also reveals the power of feedback loops. Warming caused anoxia. Anoxia produced toxic gases. Toxic gases accelerated extinction, which reduced carbon cycling, allowing greenhouse gases to accumulate further. The system reinforced its own collapse. Life did not simply fail. Earth systems overwhelmed it. This extinction reshaped evolution completely. The survivors were not the most dominant species of the Permian world, but those with broad tolerances, small size, and flexible metabolisms. These traits would define the next era of life. The Permian extinction cleared ecological space on a scale never seen before. When recovery finally began, it followed new trajectories. The age of dinosaurs would rise from this devastation not by continuity, but by replacement. The lesson of the Permian is stark. Gradual planetary change can produce sudden, irreversible collapse. Stability can persist until it does not, then everything changes at once. In the next chapter, we will explore the aftermath of the Great Dying and how life clawed its way back from the brink of near annihilation. The world that emerged after the Permian extinction was nearly unrecognizable. Forests were gone across vast regions, replaced by barren landscapes and microbial mats. Rivers carried sediment into lifeless seas stained with iron and sulfur. For millions of years, Earth existed in a state that barely supported complex life. This was not a recovery phase. It was survival mode. The immediate aftermath of the Great Dying was marked by extreme instability. Global temperatures remained high, driven by lingering greenhouse gases. Ocean circulation was weak, and oxygen levels stayed dangerously low. Toxic conditions persisted long after volcanic activity declined. The biosphere was locked in a feedback trap. It could not easily escape. Diversity was at its lowest point in hundreds of millions of years. Ecosystems that once contained thousands of interacting species were reduced to a few resilient generalists. These survivors did not form balanced food webs. Instead, they occupied simplified chains with little redundancy. Any disturbance could cause collapse again. On land, vegetation struggled to return. Soil systems had collapsed during the extinction. Without roots to stabilize, ground erosion was severe. Nutrients washed away before plants could establish long-term growth. Early recovery landscapes were dominated by opportunistic species that grew quickly and died young. This pattern, known as the disaster flora phase, appears repeatedly after mass extinctions. Plants that thrive are not those that build stable ecosystems, but those that tolerate stress, poor soils, and extreme climates. Forests do not return immediately. First comes chaos. Animals faced similar challenges. Many survivors were small, burrowing, or semi-aquatic forms capable of avoiding heat and low oxygen. Large body sizes were a disadvantage, requiring more food and oxygen than the environment could provide. Gigantism vanished. Predators were rare. Herbivores dominated simplified ecosystems, feeding on sparse vegetation, without complex predator pressure populations fluctuated wildly. Boom and bust cycles became common, further destabilizing recovery. Marine environments were even slower to heal. Anoxic conditions persisted in deep waters, preventing recolonization. Reef systems were absent, leaving no stable habitat for diverse marine communities. Shell-building organisms struggled due to altered ocean chemistry. Carbonate saturation levels were low, making it difficult for organisms to form hard shells or skeletons. This inhibited the return of many groups that had dominated pre-extinction seas. Soft-bodied organisms became more common. For several million years, life on Earth existed in a diminished state. Evolutionary innovation slowed not because mutations stopped, but because ecological opportunity was limited. There were few stable niches to fill. Yet even in this harsh world, change was underway. Greenhouse gases slowly declined as volcanic activity waned and chemical weathering resumed. Temperatures began to fall, gradually easing heat stress. Ocean circulation improved, incrementally increasing oxygen availability. These changes were slow, almost imperceptible on human timescales, but in geological terms, they marked the beginning of true recovery. Life responded cautiously. New plant lineages emerged, adapted to recovering soils. These plants stabilized landscapes, allowing more complex vegetation to develop. Once roots returned, erosion slowed, nutrient cycles re-established, and ecosystems gained structure. On land, a new generation of animals rose to prominence. Among them were early archosaurs, a group that would later include dinosaurs, birds, and crocodilians. They possessed traits that favored survival in unstable environments, upright posture, efficient lungs, and adaptable metabolisms. These traits were not designed for dominance. They were survival tools. The world they inhabited was unpredictable. Those that could endure variability thrived. Marine ecosystems followed a similar pattern. Bivalves and gastropods expanded, filling niches left empty by extinct groups. Fish diversified, cautiously exploring new feeding strategies and habitats. Recovery was uneven, patchy, and slow. This prolonged recovery phase highlights an often overlooked aspect of mass extinctions. The extinction event itself may be brief in geological terms, but its aftermath can dominate Earth history for tens of millions of years. The Permian extinction reset the evolutionary clock. It did not merely remove species. It erased ecological memory. The rules of interaction had to be rewritten from scratch. As ecosystems rebuilt, new dynamics emerged. Competition was initially low, allowing rapid diversification once conditions stabilized. This created bursts of evolution where new body plans and behaviors appeared quickly. This period of innovation marks the transition into the Triassic. The planet was still unstable, but it was no longer dead. Life was experimenting again. However, the recovery carried hidden danger. Low diversity ecosystems lack buffering capacity. With few species performing critical roles, the loss of even one can have outsized impact. The recovering biosphere was fragile. Climate remained volatile. Although cooling had begun, greenhouse conditions persisted in many regions. Extreme weather events were common. Droughts and floods alternated unpredictably, stressing young ecosystems. The atmosphere itself bore scars of extinction. Oxygen levels were lower than before, limiting body size and metabolic rates. This constrained evolution until levels gradually rose again. Despite these challenges, life pushed forward. The Triassic world became a testing ground for new forms. Reptiles diversified into terrestrial, aquatic, and aerial niches. Early mammals evolved small nocturnal lifestyles, avoiding competition and heat. This recovery phase set the stage for the next mass extinction. The same processes that allowed life to rebound also introduced new vulnerabilities. As ecosystems grew more complex, once again they approached thresholds of stability. The planet had not yet learned restraint. Geological forces remained active. Continental rifting began breaking Pangea apart. Massive volcanic events loomed once more. Earth had survived its greatest catastrophe, but survival does not guarantee safety. In the next chapter, we will examine the unstable Triassic world and the conditions that led to the extinction that would clear the path for dinosaur dominance. The Triassic world was a planet trying to reinvent itself. After the devastation of the Permian extinction, life did not return to a balanced, stable system. Instead, it rebuilt under pressure in a climate that remained volatile and unpredictable. Recovery and instability existed at the same time, shaping a world defined by extremes. Pangea still dominated the globe. Although fractures had begun to form, the supercontinent remained largely intact. Its sheer size controlled climate patterns, creating vast continental interiors, far from oceanic moderation. Heat accumulated over land, producing scorching summers, while winters remained cold and dry. Rainfall was seasonal and unreliable. Drought was common. These harsh conditions acted as a powerful evolutionary filter. Species that survived were those capable of tolerating stress. Flexibility became more valuable than specialization. The Triassic biosphere favored endurance over efficiency. Reptiles rose as the dominant vertebrates of this new world. Unlike amphibians, which required constant moisture, reptiles could reproduce away from water using shelled eggs. Their skin reduced water loss, and their physiology tolerated temperature swings. These advantages allowed them to spread across dry landscapes. Archosaurs expanded rapidly. This group included a wide range of forms, from early crocodile-like predators to agile bipedal hunters. Some evolved elongated limbs for running, others developed powerful jaws for ambush. Diversity increased, but ecosystems remained thinly connected. Early dinosaurs appeared during this time, but they were not yet dominant. They were small, rare, and often marginal members of ecosystems. More established reptile groups held most ecological roles. Early mammals existed as well, but they were tiny, nocturnal insect eaters living in the shadows. Their survival depended on avoiding competition and extreme heat. They were present, but inconsequential. Plant life also reflected the instability of the era. Forests were sparse and often dominated by drought-tolerant species. Conifers and seed ferns replaced the lush vegetation of earlier periods. Plant communities were simple and widely spaced, leaving soils exposed. This exposed land amplified environmental stress. Erosion increased sediment loads in rivers, altering coastal ecosystems. Nutrient runoff fluctuated wildly, fueling instability in marine environments. The oceans had not fully recovered from Permian anoxia. Oxygen levels improved slowly, but many deep regions remained hostile. Marine ecosystems were shallow-focused and lacked complex reef structures. Food webs were simpler and less resilient. The Triassic climate oscillated repeatedly between hot greenhouse phases and cooler intervals. These swings were driven by volcanic activity and changing atmospheric composition. Each shift stressed ecosystems already operating near their limits. Beneath the surface, Earth's interior was again becoming restless. Mantle plumes rose beneath the edges of Pangea as rifting began. Pressure built beneath what would eventually become the Atlantic Ocean. This tectonic activity produced massive volcanic provinces, releasing carbon dioxide, sulfur dioxide, and other gases into the atmosphere. Unlike the Siberian traps, these eruptions were distributed over time, but their cumulative impact was profound. Carbon dioxide levels rose rapidly, intensifying greenhouse warming. Temperatures climbed, pushing ecosystems toward heat thresholds. Warm oceans held less oxygen, expanding anoxic zones once again. Acid rain from sulfur emissions damaged vegetation and altered soil chemistry. Forests weakened already, struggling in arid conditions. Plant loss destabilized food chains and increased erosion further. The Triassic extinction did not arrive suddenly. It crept forward through repeated environmental shocks. Each volcanic pulse weakened ecosystems that had little capacity to absorb disturbance. Marine life suffered greatly. Many remaining reef-building organisms disappeared permanently. Ammonoids experienced repeated losses. With only a few lineages surviving, fish communities simplified. On land, large amphibians vanished, unable to cope with heat and drought. Many reptile groups that had thrived earlier declined rapidly. Extinction selectively removed established competitors. This selective loss reshaped ecosystems profoundly. As dominant groups disappeared, ecological space opened. Species that had previously been minor players suddenly found opportunity. This is where dinosaurs began to rise. They possessed traits well suited to the changing world. Efficient respiration allowed higher activity levels in low oxygen conditions. Upright posture reduced heat stress. Rapid growth allowed quick reproduction and adaptation. Dinosaurs did not outcompete others through superiority alone. They inherited a cleared landscape. Extinction removed their rivals. This pattern is central to understanding evolutionary dominance. Success often follows catastrophe, not innovation. Mass extinctions do not reward the best adapted species of stable times. They reward those suited to chaos. By the end of the Triassic extinction, many reptile groups were gone. The world entered the Jurassic with ecosystems simplified but open. Dinosaurs expanded rapidly, filling roles from apex predators to massive herbivores. The Triassic-Jurassic boundary marks another global extinction event. It was not as severe as the Permian, but it was decisive. It reshaped terrestrial ecosystems permanently. Volcanic activity associated with continental breakup played a central role. Massive lava flows covered large regions, and atmospheric chemistry shifted dramatically. climate warming accelerated. This extinction highlights an important principle. Tectonic processes can drive biological collapse not through a single event, but through prolonged stress. Gradual change can be as lethal as sudden disaster. Life, once again, survived, but at a cost. Biodiversity declined, ecosystems simplified, and evolutionary trajectories shifted. The age of dinosaurs began not because dinosaurs were destined to rule, but because extinction cleared the way. The Triassic world reminds us that recovery from extinction does not restore safety. It builds new systems that carry their own vulnerabilities. Each recovery plants the seeds of the next collapse. Earth had now experienced 4 mass extinctions. Each one reshaped life more dramatically than the last. Complexity increased vulnerability, and the margin for error narrowed. The planet was entering a long period of relative stability in the Jurassic and Cretaceous. Dinosaurs would dominate and ecosystems would flourish. But beneath that success, a final catastrophe waited. In the next chapter, we will explore the Cretaceous world at its peak, a planet teeming with life just before the last great extinction ended the age of dinosaurs. By the late Cretaceous, Earth had reached one of the most biologically rich moments in its entire history. Ecosystems were dense, layered, and highly interconnected. Life occupied land, sea, and sky with an efficiency never seen before. From a distance, the planet appeared stable, even prosperous. Yet this abundance concealed a growing fragility. The climate of the Cretaceous was warm and humid. There were no permanent polar ice caps. Forests extended into high latitudes, and sea levels were among the highest in Earth history. Shallow inland seas split continents, creating vast coastlines and nutrient-rich habitats. Productivity was immense. Dinosaurs dominated terrestrial ecosystems. They filled every major ecological role. Massive herbivores reshaped landscapes through feeding and migration. Apex predators regulated populations and drove evolutionary arms races. Smaller dinosaurs occupied niches ranging from scavengers to agile hunters. This dominance was not static. Dinosaurs continued to evolve rapidly. Feathers, insulation, complex behaviors, and advanced sensory systems became common. Many lineages showed high specialization adapted to specific environments and food sources. Plants also transformed the planet. Flowering plants spread rapidly, altering ecosystems fundamentally. They diversified into countless forms, producing fruits, seeds, and flowers that reshaped food webs. Insects.co evolved with plants, accelerating diversification on both sides. This biological explosion increased interdependence. Species relied on precise timing, pollination relationships, and stable climates. Food webs became intricate, efficient, and vulnerable. The oceans mirrored this complexity. Marine reptiles ruled as apex predators. Ammonites thrived in immense numbers. Plankton supported vast food chains that fed fish, reptiles, and early birds. Coral reef systems flourished in warm, shallow seas. Yet beneath this abundance, Earth systems were shifting again. Volcanic activity increased, particularly in what is now India, where massive eruptions began forming the Deccan Traps. Lava flows released large amounts of carbon dioxide and sulfur gases, altering climate and ocean chemistry. These eruptions unfolded over hundreds of thousands of years, stressing ecosystems gradually. Warming trends intensified, ocean acidification increased, and oxygen levels fluctuated. Extinction pressures began mounting before the final catastrophe arrived. Evidence from fossils shows biodiversity declining unevenly in the final million years of the Cretaceous. Some groups were already struggling. Reef systems weakened and certain plankton populations declined. The biosphere was under stress. Still life persisted. Ecosystems adapted as they had many times before. Evolution adjusted ranges, behaviors, and physiology. From within, the system collapse did not seem inevitable. Then a new force entered the equation. Approximately 66 million years ago, an asteroid roughly 10 kilometers wide struck Earth. It impacted in shallow seas, releasing energy equivalent to billions of nuclear weapons. The collision vaporized rock, water, and life, instantly creating a crater over 100 kilometers wide. The immediate effects were regional and absolute. Everything within hundreds of kilometers died in seconds. Shockwaves, earthquakes, and tsunamis radiated outward, devastating coastlines across the globe. But the true extinction mechanism was not the impact itself. It was what followed. The collision ejected vast quantities of dust, soot, and aerosols into the atmosphere. Sunlight was blocked, plunging the planet into darkness. Temperatures dropped rapidly, initiating an impact winter that lasted months to years. Photosynthesis collapsed, plants died on land, and phytoplankton died in the oceans. Food chains disintegrated from the base upward. Herbivores, starved predators followed. Global firestorms ignited by re-entering debris burned forests worldwide, adding more soot to the atmosphere. Oxygen levels dropped, carbon cycles broke down, and ecosystems unraveled. Ocean chemistry shifted dramatically. Acid rain fell, globally altering soils and freshwater systems. Surface waters cooled, while deep oceans remained warm, disrupting circulation patterns and reducing oxygen further. Species with high metabolic demands, large body sizes, or specialized diets were hit hardest. Dinosaurs, except for a small lineage of birds, could not survive prolonged food shortages. Large marine reptiles vanished. Ammonites disappeared entirely. Yet not all life died. Small, adaptable organisms with broad diets and the ability to shelter survived. Mammals, birds, crocodilians, turtles, and many fish endured the darkness. This selective survival reshaped evolution. Size became a liability. Specialization became weakness. Flexibility was everything. Within a geological instant, the age of dinosaurs ended. Ecosystems that had dominated for over 100 million years vanished. The Cretaceous Paleogene extinction was not the largest in terms of percentage loss, but it was among the most sudden. The speed of collapse gave life little time to adapt. Recovery would again take millions of years. This extinction illustrates a different trigger than previous events. Unlike climate-driven collapses, this was an external shock, a random cosmic event intersected with a stressed biosphere. Timing mattered. Had the asteroid struck during a more resilient period, life might have recovered faster, but it arrived during a phase of volcanic stress and ecological fragility. The system was already near a tipping point. The extinction did not end evolution. It redirected it. Mammals expanded rapidly into empty niches. Birds diversified, inheriting aerial ecosystems. Flowering plants reshaped landscapes once again. The world that followed was quieter, smaller, and less dominated by giants. Ecosystems rebuilt around new rules. This final mass extinction closes the era of ancient worlds. It marks the boundary between deep time ruled by reptiles and the modern world shaped by mammals. Yet, it also raises a troubling question. If extinction can be triggered by random forces beyond planetary control, then stability is always temporary. Earth had now endured 5 mass extinctions. each one different in cause, but similar in outcome. Collapse followed by recovery, replacement, and transformation. In the final chapter, we will look beyond the past and ask whether the patterns written into Earth history are repeating once more. When the dust finally settled after the asteroid impact, Earth entered a long, quiet aftermath. The sky cleared slowly, sunlight returned, and temperatures began to stabilize. But the world that re-emerged was stripped of its former complexity. Forests were sparse, oceans were simplified, and food webs had been shattered. The Cretaceous-Paleogene boundary marks not only an extinction, but the beginning of a prolonged rebuilding of the biosphere. The immediate post-impact world was defined by scarcity. Photosynthesis had collapsed for months or years, and many plant lineages were gone. The plants that survived were those capable of rapid growth and reproduction. Ferns became especially common, creating what scientists call a fern spike, a signal of ecological reset. Forests did not return immediately. First came ground cover, then shrubs, then trees over millions of years. With vegetation reduced, herbivores remained small and few. Large body size was no longer viable. Ecosystems favored animals that required little food, could reproduce quickly, and could exploit a wide range of resources. This shift fundamentally altered the direction of evolution. Mammals were among the greatest beneficiaries of this new world. During the age of dinosaurs, mammals had existed mostly in the margins, small, nocturnal, and ecologically constrained. Extinction removed their competitors almost overnight. Suddenly, vast ecological space lay empty. Mammals diversified rapidly. Body sizes increased, diets expanded, and new forms evolved to fill roles once held by dinosaurs. Herbivores, carnivores, burrowers, climbers, swimmers all emerged from small ancestral lineages. Evolution accelerated because opportunity was everywhere. Birds followed a similar path. The avian dinosaurs that survived the extinction inherited the skies. They diversified into countless forms, adapting to new food sources and habitats. Flight became a powerful advantage in a recovering world. Marine ecosystems rebuilt more slowly. Plankton communities took time to re-establish, delaying recovery up the food chain. Coral reef systems were absent for millions of years, leaving oceans less diverse and more fragile. Eventually, new reef builders evolved, but the ecosystems were fundamentally different from those of the Cretaceous. This recovery phase reveals a consistent pattern across mass extinctions. The biosphere does not simply resume where it left off. It reorganizes under new constraints. Winners are not those that dominated before, but those that exploit new conditions. Climate during the early Paleogene was warm. Greenhouse conditions returned with high carbon dioxide levels. Tropical forests spread widely, and polar regions supported temperate ecosystems. This warmth allowed rapid biological expansion. Yet even as life flourished again, Earth systems continued their slow cycles. Tectonic plates shifted, opening and closing seaways. Ocean currents changed, redistributing heat. Climate fluctuated between warm and cooler phases. Extinction had not ended instability. Over tens of millions of years, ecosystems regained complexity. Food webs deepened, redundancy increased, and resilience slowly returned. Mammals grew larger, occupying apex predator roles. Grasslands eventually spread, reshaping terrestrial ecosystems again. This long recovery sets the stage for the modern world. The continents assumed recognizable positions, climate stabilized into familiar patterns, and biodiversity increased. From a human perspective, Earth appears stable. But mass extinctions are not anomalies in Earth history. They are recurring features. The same processes that drove past collapses continue today. Climate change, ocean acidification, habitat loss, and atmospheric alteration are active forces once more. The difference now is speed. Past mass extinctions unfolded over thousands to millions of years. Current changes are happening within centuries. Life has little time to adapt. Human activity is altering Earth systems at a scale comparable to geological forces. Greenhouse gas emissions rival those of major volcanic events. Deforestation mirrors past ecosystem collapses. Ocean anoxia and acidification resemble conditions seen during previous extinctions. Many scientists argue that we are entering a sixth mass extinction. Species loss rates far exceed background levels. Ecosystems are fragmenting and climate thresholds are being crossed. History does not repeat exactly, but patterns persist. High specialization, interdependence, and rapid environmental change are the same ingredients that preceded past collapses. The fossil record shows that life will survive. Microbes, plants, and adaptable animals will persist. But the world that follows will be different. Many species, including possibly humans, may not be part of it. Earth's 5 mass extinctions are not just stories of the past. They are warnings written into the structure of the planet. They show that stability is temporary and that life exists within limits. This chapter completes the long arc from origin to collapse to recovery. The planet has endured unimaginable loss, and yet life continues to adapt. The final question is not whether Earth will survive. It always has. The question is whether the world we know will. The rise of mammals did not happen in a single dramatic leap. It unfolded slowly through experimentation, adaptation, and failure across millions of years. The post-extinction world offered opportunity, but it also imposed limits. Ecosystems were still fragile, climates still unstable, and competition gradually returned. Survival required more than luck. It required flexibility. Early mammals were not immediately dominant. Many lineages tried and failed. Some grew too large, too fast, and vanished. Others specialized too narrowly and disappeared when climates shifted. What endured were lineages that balanced innovation with restraint. One of the defining features of mammalian success was adaptability. Mammals evolved diverse feeding strategies, teeth, shapes, and digestive systems, allowing them to exploit plants, insects, meat, and mixed diets. This dietary flexibility reduced dependence on any single food source. Endothermy allowed mammals to regulate body temperature. This was energetically costly, but it allowed activity across a wider range of climates and times of day. Mammals could forage at night during cold periods and survive seasonal extremes more effectively than many competitors. Reproduction also played a role. Live birth and parental care increased survival rates of offspring in unstable environments. Investing in fewer, well-protected young proved advantageous during periods of ecological uncertainty. As mammals, diversified ecosystems regained structure. Predator-prey dynamics, re-established plant-herbivore interactions stabilized, and nutrient cycles strengthened. Forests returned, grasslands spread, and soils deepened. Earth was rebuilding complexity once again, yet this rebuilding carried inherent risk. As ecosystems become more complex, they also become more interdependent. The same vulnerability that existed before past extinctions was returning. Climate during the Cenozoic era fluctuated significantly. Periods of intense warmth were followed by gradual cooling. Polar ice caps formed for the first time in tens of millions of years. Sea levels dropped, reshaping coastlines and habitats. These shifts drove evolution, but also caused localized extinctions. Species adapted to warm climates retreated or vanished as cooling progressed. Others expanded. Extinction did not stop after the fifth mass extinction. It continued at background levels, shaping biodiversity constantly. Grasslands expanded during cooler, drier periods, favoring grazing animals. This transformation altered food webs, again leading to new adaptations such as high-crowned teeth and herd behavior. Predators evolved speed and endurance to hunt across open landscapes. Among the mammals, evolving during this time were primates. Initially, small arboreal creatures adapted to forest canopies. They developed grasping hands forward, facing eyes, and complex social behaviors. These traits would later become central to human evolution. Primates were not destined to dominate. Many lineages vanished during climate shifts. Survival depended on flexibility, social cooperation, and intelligence. As Africa dried, forests fragmented, forcing primates out of trees and into open environments. Bipedalism emerged as an adaptation to long-distance travel, heat regulation, and carrying food. Again, necessity drove innovation. The human lineage represents one of many evolutionary experiments. It succeeded not because of physical superiority, but because of cognitive flexibility. Tool use, social learning, and cooperation allowed humans to adapt faster than genetic evolution alone. This ability to modify environments, however, introduced a new dynamic. Humans did not merely adapt to Earth's systems, they began altering them intentionally. Fire, agriculture, and settlement reshaped landscapes. Megafauna declined in regions where humans arrived. Whether through hunting, habitat change, or climate interaction, large animals vanished rapidly. These losses resemble localized mass extinctions. The pace of change accelerated further with industrialization. Fossil fuels released carbon stored for hundreds of millions of years back into the atmosphere within centuries. This rapid input overwhelmed natural carbon cycles. Climate warmed oceans, acidified ice melted, and sea levels rose. Ecosystems fragmented under pressure from deforestation, pollution, and overexploitation. Extinction rates climbed sharply. What distinguishes the current era is not that extinction is occurring, but how quickly past mass extinctions unfolded over thousands to millions of years. Current biodiversity loss is happening within a few human generations. This speed limits evolutionary response. Species cannot adapt genetically at the pace environments are changing. Migration is blocked by human infrastructure. Ecological escape routes are closing. The planet itself is responding as it always has. Climate feedbacks amplify warming, ice loss reduces reflection, permafrost releases methane, Earth systems shift toward new equilibria, regardless of human preference. From a geological perspective, humanity has become a force comparable to volcanism or asteroid impacts. The difference is agency. This is the first mass extinction driven by a single species with awareness of its actions. The fossil record of the future will show a sharp boundary. Sudden loss of large animals, rapid climate change, altered sedimentation patterns, and chemical signatures in rock layers. Future geologists will not need legends to identify this moment. The question is not whether Earth will recover. It always does. The question is what survives into that future. Past extinctions show that life rebounds but not on human timescales. Recovery takes millions of years. Civilizations do not survive those intervals. Chapter 11 is not an ending, it is a convergence. All 5 mass extinctions point toward a central lesson. Earth tolerates change, but not excess speed. When thresholds are crossed, collapse follows. The planet does not care who causes extinction. It responds the same way every time. Life adapts or disappears. What remains uncertain is whether intelligence will become a survival trait or another evolutionary dead end. The history of mass extinctions does not predict the future precisely, but it defines the boundaries within which the future will unfold. Earth has reset itself before. It can do so again. The concept of mass extinction often feels distant, abstract, and ancient. Yet, the processes that drive it are not locked in the past. They are mechanisms of the planet itself, recurring whenever certain conditions align. Chapter 12 moves away from specific historical events and focuses on the pattern that connects them all. This is the anatomy of extinction. Every mass extinction begins long before the visible collapse. The fossil record shows that ecosystems rarely fail without warning. Chemical signatures shift biodiversity, plateaus, then declines, and stress indicators accumulate quietly. Extinction is not an event, it is a process. One of the earliest signals is environmental imbalance. Carbon cycles destabilize oxygen levels, fluctuate, and climate variability increases. These changes may appear minor initially, but they strain organisms already adapted to narrow conditions. Stress weakens populations, making them vulnerable to additional shocks. Specialization plays a central role. In stable environments, evolution favors efficiency. Species evolve to exploit specific resources, habitats, and conditions. This creates highly productive ecosystems, but also rigid ones. When conditions change, specialists struggle to adapt. Generalists, on the other hand, trade efficiency for flexibility. They may be less competitive during stable periods, but they survive disruption. This is why survivors of mass extinctions are often small, adaptable, and unspecialized. Another common feature is connectivity. As ecosystems grow more complex, they become more interdependent. Food webs deepen, nutrient cycles tighten, and mutual dependencies increase. This complexity increases productivity but reduces resilience. When one component fails, others follow. This is known as cascading collapse. The loss of a keystone species can destabilize entire ecosystems. During mass extinctions, multiple keystones fail simultaneously, overwhelming recovery mechanisms. Rate of change is critical. Life can adapt to gradual shifts through migration, mutation, and selection. But when change accelerates, adaptation fails. Geological records show that rapid climate shifts correlate strongly with extinction intensity. All 5 mass extinctions involve rapid environmental change relative to evolutionary timescales. Whether driven by volcanism, glaciation, ocean anoxia, or asteroid impact, the common factor was speed. Another shared element is feedback loops. Once stress begins, it often triggers processes that amplify it. Warming reduces oxygen solubility, causing anoxia, which kills organisms that regulate carbon cycling, leading to further warming. Extinction accelerates itself. These feedbacks push systems past tipping points. Beyond these thresholds, recovery becomes extremely difficult, even if the original trigger subsides. This is why post-extinction worlds remain unstable for millions of years. Mass extinctions also reveal that life can be both victim and cause. Biological innovations such as oxygenic photosynthesis or land plant expansion altered Earth systems dramatically. Life reshaped the planet in ways that eventually exceeded its own tolerance. This interaction between biology and geology is central to Earth history. The planet is not a passive stage. It responds to life, and life responds in return. When feedbacks align, extinction follows. Geography also matters. Supercontinent formation alters climate, ocean circulation, and habitat distribution. Pangea played a key role in the Permian and Triassic extinctions by amplifying extremes and reducing ecological refuges. Oceans are particularly sensitive. Most mass extinctions hit marine life hardest because oceans integrate global changes quickly. Temperature, oxygen, and chemistry shifts propagate rapidly, affecting vast areas simultaneously. Anoxia appears repeatedly in extinction records. Oxygen loss suffocates ecosystems and promotes toxic microbial activity. Once widespread anoxia develops, recovery is slow because oxygenation requires circulation stability. The fossil record shows that reefs are early casualties. Reef ecosystems collapse in nearly every mass extinction and take the longest to recover. Their sensitivity makes them indicators of planetary stress. Terrestrial ecosystems often collapse slightly later following marine declines. This lag reflects the buffering capacity of land systems, but once collapse begins, it is rapid. Extinction selectivity is another key feature. Mass extinctions do not kill randomly. They target certain traits repeatedly. Large body size, high metabolic demand, narrow temperature tolerance, and specialized diets increase risk. Survival traits recur across extinctions. Small size, broad diet, flexible reproduction, and ability to shelter increase survival odds. These traits shape post-extinction evolution. After extinction recovery begins, but not immediately, environmental conditions must stabilize first. Until then, ecosystems remain locked in low diversity states, dominated by opportunistic species. Recovery is constrained by missing interactions. When pollinators, predators, or symbiotic partners are gone, ecosystems cannot rebuild fully. This ecological memory loss slows evolution. When recovery does occur, it often follows bursts. Vacant niches allow rapid diversification. Evolutionary innovation accelerates, but within new boundaries defined by altered climates and geographies. Importantly, recovery does not restore the previous world. It creates a new one. Each mass extinction permanently redirects evolution. Dominant groups disappear, new ones arise, and ecological rules change. This is why Earth history is divided into eras, separated by extinction boundaries. These are not arbitrary divisions. They mark fundamental reorganizations of life. Chapter 12 emphasizes that mass extinctions are not failures of life, but consequences of planetary dynamics. Earth is capable of sustaining life, but not indefinitely under all conditions. The planet does not aim for biodiversity. It responds to energy flows, chemical gradients, and physical laws. Life persists only while it fits within those constraints. This perspective reframes extinction from tragedy alone to transformation. Loss and creation are intertwined. Yet, this does not diminish the severity of collapse. Extinction erases unique evolutionary histories permanently. Understanding the anatomy of extinction is essential because it reveals that no species, no matter how dominant, is exempt. Trilobites, Dinosaurs, reef builders, and apex predators all vanished when conditions shifted beyond tolerance. This knowledge challenges the assumption of permanence. Dominance is temporary. Stability is conditional. The final chapters will turn fully toward the present. With this framework in place, the similarities between past extinctions and current trends become impossible to ignore. The same signals are appearing again. Environmental imbalance, accelerating change, specialization, connectivity, and feedback loops are all active. The difference this time is not the mechanism, it is the agent. In the next chapter, we will confront the modern world through the lens of deep time and ask whether the sixth mass extinction has already begun. If future scientists were to study the present from millions of years ahead, they would not begin with headlines or historical records. They would begin with rocks, ice cores, and chemical signatures. And what they would see is unmistakable. A sharp disruption in Earth systems compressed into an extraordinarily short span of time. Chapter 13 examines the modern era not as a moral story, but as a geological event. Background extinction is a constant. Species appear and disappear at low rates, driven by competition, migration, and gradual environmental change. This is the normal rhythm of life. Mass extinction is different. It is defined by magnitude and speed. The current rate of species loss far exceeds background levels. In geological terms, it is abrupt. The causes are not hidden. Atmospheric carbon dioxide has risen faster than at any time in at least 66 million years. Global temperatures are climbing, ocean chemistry is changing, and habitats are fragmenting. These are the same stressors that preceded past mass extinctions. The difference is scale of time. Processes that once unfolded over tens of thousands of years are now occurring within centuries. Life has no precedent for adapting this quickly. Climate change is the most visible driver. Warming alters temperature ranges, precipitation patterns, and seasonal timing. Species adapted to narrow climates are pushed beyond tolerance limits. Migration routes shift, but are often blocked by human infrastructure. Isolated populations decline and vanish. Warming also destabilizes weather systems. Droughts, floods, and heat waves increase in frequency and intensity. These extremes cause sudden population crashes rather than gradual decline. Ecosystems experience repeated shocks without recovery time. Oceans absorb much of the excess heat and carbon dioxide. This buffering slows atmospheric warming, but creates new problems. Warmer oceans hold less oxygen, leading to expanding dead zones. Acidification interferes with shell and skeleton formation, affecting plankton, corals, and shellfish. These marine changes mirror conditions seen during past extinctions, especially the Devonian and Permian reefs are once again among the first casualties. Coral bleaching events occur globally with increasing frequency, leaving ecosystems unable to recover between episodes. Habitat loss compounds these stresses. Deforestation, agriculture, urbanization, and mining fragment ecosystems into isolated patches. Small populations lose genetic diversity, increasing extinction risk. Corridors that once allowed migration no longer exist. Overexploitation accelerates collapse. Fishing, hunting, and harvesting remove species faster than they can reproduce. Large animals are especially vulnerable due to slow reproductive rates. Megafauna declines, echo patterns seen at the end of the Pleistocene when human expansion coincided with widespread large animal extinctions. Invasive species further destabilize ecosystems. Transported intentionally or accidentally, they outcompete native species lacking defenses. This homogenizes biodiversity, reducing resilience and increasing vulnerability to environmental change. Pollution introduces novel stressors. Chemicals, plastics, and heavy metals accumulate in food webs, disrupting physiology and reproduction. These factors rarely act alone. They interact, amplifying each other. This convergence of pressures is what defines mass extinction. No single cause is responsible. It is the alignment of multiple stressors overwhelming adaptive capacity. From a geological perspective, the human era represents a sudden spike in energy release and material movement. Fossil fuel combustion mobilizes carbon stored for hundreds of millions of years. Mining and construction move more sediment annually than natural erosion processes. Rivers are dammed, coastlines reshaped, and nutrient cycles altered. These signatures will persist in rock layers long after human societies are gone. Isotopic anomalies, plastic residues, and abrupt extinction horizons will mark this interval clearly. The question of whether this qualifies as a sixth mass extinction depends on thresholds. Some scientists argue it is already underway. Others say it is in its early stages. Geology, however, is indifferent to labels. What matters is trajectory. Past extinctions show that once certain feedbacks engage, reversal becomes extremely difficult. Warming triggers ice loss, which accelerates warming. Ecosystem loss reduces carbon uptake, increasing atmospheric concentrations. Permafrost thaw releases methane, amplifying greenhouse effects. These feedbacks are now active. The system is responding predictably based on physical laws, not political decisions. One critical difference remains: awareness. Humans possess knowledge of these processes. No previous extinction agent understood its role. This introduces a unique variable, but not a guarantee of prevention. Knowledge does not automatically produce change. Evolutionary history shows that dominant species rarely relinquish advantage voluntarily. Adaptation often comes too late. Technology complicates the picture. It allows rapid exploitation, but also potential mitigation. Renewable energy conservation and ecosystem restoration could slow trends. Whether these actions occur at sufficient scale and speed remains uncertain. From a deep time perspective, the outcome is binary. Either stressors stabilize before tipping points are crossed, or collapse accelerates. There is no partial extinction in geological terms. Thresholds define outcomes. If collapse proceeds, life will not end. Microbes, plants, insects, and adaptable animals will survive. Biodiversity will eventually rebound. But the composition of life will change dramatically. Humans may persist in some form, or they may join the long list of dominant species that reshape the planet only to vanish. Intelligence does not exempt species from extinction. Adaptability does. This chapter does not argue inevitability. It argues constraint. Earth systems operate within limits. Exceeding them produces predictable results. The fossil record shows that recovery from mass extinction takes millions of years. Ecosystems rebuild slowly through evolutionary processes that cannot be accelerated. Civilization dependent on stable climate, agriculture, and biodiversity cannot survive that interval unchanged. The modern era is therefore not unique in outcome, but in responsibility. This is the first time a single species has altered planetary systems knowingly. The past does not judge, it informs. Chapter 13 reframes the present as a moment within Earth history rather than outside it. The same forces are at work, the same thresholds approach. Whether this becomes the sixth mass extinction is still undecided, but the window for divergence is narrow. The next chapter will examine possible futures not as predictions, but as pathways shaped by choices, physical laws, and deep time patterns. The planet has followed these paths before. The question is, which one it follows next. When scientists imagine the future of life on Earth, they do not rely on speculation alone. They look backward. The fossil record does not predict exact outcomes, but it defines boundaries. Chapter 14 explores the possible futures that emerge from those boundaries, not as science fiction, but as trajectories constrained by physical law and evolutionary history. Earth systems operate on momentum. Once set in motion, they do not stop instantly. Greenhouse gases already released will continue to influence climate for centuries. Oceans will continue absorbing heat long after emissions slow. Ice sheets respond slowly, but once destabilized, they can collapse rapidly. This inertia means the future is shaped by past actions, whether or not new actions are taken. One possible future is stabilization. In this scenario, greenhouse gas concentrations peak, then decline. Warming slows, ecosystems are given time to adapt, and extinction rates remain elevated but do not accelerate into full mass extinction. Biodiversity declines, but core ecological functions persist. This pathway requires rapid, large-scale change in energy systems, land use, and consumption patterns. From a geological perspective, it represents an interruption of a developing extinction trajectory before major tipping points are crossed. The fossil record shows that such interruptions are rare, but not impossible. Earth systems can stabilize when feedbacks are weakened. Reduced carbon input allows weathering and biological uptake to restore balance. Oceans slowly re-oxygenate, climates settle into new but livable states. Life under this future would be different but recognizable. Many species would be lost, but large ecosystems would remain intact. Humans would persist as part of a diminished but functioning biosphere. Another pathway is partial collapse. Here, warming continues beyond safe thresholds for many ecosystems, but does not reach the extremes seen in the Permian. Coral reefs largely disappear, tropical forests fragment, and polar ice loss accelerates sea level rise. Under this, future biodiversity loss becomes severe. Food webs simplify, and many specialized species vanish. Ecosystems shift toward generalist-dominated systems with lower productivity and resilience. This world would be hotter, more unstable, and less diverse. Human societies would be forced to adapt to frequent environmental disruption. Agriculture would shift regions, water scarcity would increase, and coastal populations would retreat. From a geological perspective, this would resemble prolonged extinction intervals seen in the Devonian or Triassic. Not a single collapse, but extended stress and attrition. The third pathway is full mass extinction. This occurs if feedbacks accelerate beyond control. Widespread ice loss releases additional greenhouse gases, permafrost, methane pulses intensify warming, and ocean anoxia expands dramatically. Under these conditions, extinction cascades through marine and terrestrial systems. Large animals disappear, ecosystems collapse, and global biodiversity drops sharply within a few thousand years. This would mark a clear boundary in the fossil record. A sudden reduction in species diversity, abrupt chemical shifts, and a long recovery interval would define it unmistakably. Life would survive, but recovery would take millions of years. The biosphere would reorganize around new dominant groups, likely smaller, simpler, and more resilient to heat and low oxygen. Humans may or may not survive such a transition. Geological history suggests that highly specialized, large-bodied species dependent on stable climates are vulnerable. Intelligence alone does not guarantee survival. These futures are not choices in a moral sense. They are outcomes determined by energy flows, feedback strength, and response speed. Earth does not negotiate, it reacts. One of the most important insights from past extinctions is that prevention is far easier than recovery. Once collapse begins, reversing it is extraordinarily difficult. Ecosystems have tipping points beyond which self-correction fails. Another insight is that recovery creates new worlds, not restored ones. Even if life rebounds, it does so under different conditions with different dominant species. Extinction permanently alters evolutionary trajectories. This challenges a common assumption. Saving the planet does not mean preserving current ecosystems indefinitely. It means avoiding collapse beyond adaptability thresholds. From deep time perspective, humans occupy a narrow window. We exist during a period when planetary systems are still within a range that supports complex life and large-scale civilization. That window is not permanent. Mass extinctions reveal that Earth can exist in states hostile to complex life for tens of millions of years. Recovery is slow because rebuilding complexity requires stable conditions and long evolutionary timescales. The future, therefore, hinges on speed. Slowing change allows adaptation, accelerating change overwhelms it. This principle applies regardless of cause. Technological optimism often assumes humans can engineer solutions faster than geological processes unfold. The fossil record offers caution. No species has ever outpaced planetary-scale feedbacks once fully engaged. However, technology can alter trajectories if applied early and broadly. Reducing emissions, restoring ecosystems, and preserving biodiversity can weaken feedbacks. These actions do not require perfection, only sufficient scale and speed. The question becomes whether societal change can occur faster than environmental change. This is not a scientific question alone. It is a systemic one, involving economics, politics, and behavior. From Earth history perspective, societies are transient, but ecosystems persist. Geological time does not measure success in centuries, but in stability across millions of years. This reframes the idea of progress. Progress that destabilizes life support systems is not sustainable in deep time. It is a short-lived anomaly. Chapter 14 emphasizes that the future is constrained but not predetermined. Paths diverge early, then converge once thresholds are crossed. The earlier divergence occurs, the wider the range of outcomes. If humanity stabilizes its impact, Earth will still change. Climates will shift, sea levels will rise, and some species will vanish, but life will retain much of its complexity. If stabilization fails, Earth will move toward another extinction cycle. The planet will recover eventually, but not in ways that favor current life forms. Deep time teaches humility. Dominant species often assume permanence. None have been permanent. The fossil record does not show mercy or malice. It shows cause and effect. In the next chapter, we will step back one final time and view Earth's 5 mass extinctions as a single continuous story, not separate disasters, but chapters of the same planetary process. Only from that distance does their full meaning become clear. When viewed individually, Earth's 5 mass extinctions appear distinct, separated by hundreds of millions of years and driven by different causes: ice ages, volcanism, ocean anoxia, asteroid impact. Yet when viewed together from deep time, they form a single continuous story. Chapter 15 brings these events into alignment and reveals what they collectively say about the planet itself. Earth is not a static world, interrupted by occasional disasters. It is a dynamic system constantly adjusting to internal and external forces. Mass extinctions are not anomalies. They are inflection points, moments when gradual change crosses thresholds that life cannot endure. Each extinction follows the same broad sequence. Stability allows complexity to grow. Complexity increases interdependence. Interdependence reduces resilience. Environmental stress accumulates. Thresholds are crossed. Collapse accelerates. Recovery follows under new conditions. The Ordovician extinction showed that climate alone can dismantle global ecosystems. Slow cooling combined with sea level change erased most marine life. The lesson was clear. Even gradual shifts can become lethal when they restructure habitats faster than organisms can adapt. The Devonian extinction revealed that life itself can destabilize the planet. The spread of forests altered carbon cycles, ocean chemistry, and oxygen levels. Biological success pushed Earth systems beyond stable ranges. Extinction followed, not from failure, but from overreach. The Permian extinction demonstrated the power of feedback loops. Volcanism triggered warming. Warming caused anoxia. Anoxia released toxins. Toxins accelerated extinction. Once engaged, these loops became self-sustaining. The biosphere nearly collapsed entirely. The Triassic extinction showed that recovery does not guarantee safety. Life rebuilt on unstable foundations. Tectonic stress and prolonged volcanism eliminated many survivors and cleared the way for new dominance. Extinction acted as a filter, reshaping evolution again. The Cretaceous extinction proved that external forces matter. A single cosmic event intersected with an already stressed biosphere and ended the reign of dominant life forms in an instant. Randomness played a role, but vulnerability determined outcome. Taken together, these events define the operating limits of life on Earth. They show that biodiversity thrives within boundaries. When those boundaries are exceeded, collapse is not a possibility, but an outcome. One of the most striking patterns is that mass extinctions become more transformative over time. Early extinctions reshaped marine ecosystems. Later ones reorganized the entire biosphere, including land and atmosphere. As life became more complex, the consequences of collapse grew larger. This escalation is not coincidence. Complexity increases energy flow. Energy flow increases sensitivity. Complex systems operate near optimal efficiency, but with reduced tolerance for disruption. Another pattern is asymmetry. Destruction is fast, recovery is slow. Extinction can occur in thousands of years or less. Recovery requires millions. This asymmetry shapes Earth history. Collapse leaves long shadows. Mass extinctions also reveal that dominance is temporary. Trilobites once ruled the seas. They vanished. Reef builders dominated multiple eras. They collapsed repeatedly. Dinosaurs reigned for over 100 million years. They fell in an instant. Mammals rose. Their future remains uncertain. There is no final dominant form. Evolution does not move toward permanence. It moves toward occupancy until conditions change. This perspective dissolves the idea of progress as a linear ascent. Evolution is adaptive, not directional. Complexity emerges when conditions allow and disappears when they do not. Earth history also shows that life does not prevent extinction by its presence. Life often amplifies stress through feedbacks. Oxygen, photosynthesis, forest expansion, and carbonate formation all altered planetary systems dramatically. Life shapes Earth, but does not control it. This reframes the relationship between biology and geology. They are not separate domains. They are intertwined processes. Mass extinctions occur when their interaction destabilizes the system as a whole. From this view, humans are not an anomaly. They are a continuation of a pattern, a species that has become a geological force altering carbon cycles, nutrient flows, and climate. The difference lies in speed and awareness, not in mechanism. The fossil record suggests that awareness alone does not guarantee survival. Many species adapted successfully to stable conditions and failed when those conditions changed. Intelligence is useful only if it alters outcomes before thresholds are crossed. Mass extinctions also highlight the importance of refuges. During each collapse, certain environments provided shelter. Deep oceans, burrows, polar regions, and isolated habitats preserved lineages that later repopulated the planet. Survival was uneven geographically. This implies that extinction is rarely absolute. Pockets of life endure, but these pockets shape the future disproportionately. The survivors define what comes next. This is why post-extinction worlds often feel alien compared to what preceded them. They are built from remnants, not continuations. Chapter 15 emphasizes that Earth's history is not a collection of random disasters. It is a record of system behavior under stress. Mass extinctions mark moments when the planet changed state. These state changes are irreversible on human timescales. Once ice caps form or vanish, once atmospheric composition shifts, once dominant lineages disappear, the system does not simply revert. This has implications for how we understand stability today. The current world is not the default state of Earth. It is one of many configurations the planet has passed through. Deep time teaches that the planet is comfortable with extremes. It has been ice-covered and hothouse, oxygen-poor and oxygen-rich, dominated by microbes, reptiles, and mammals. None of these states are permanent. What persists is change. Yet within this constant change, patterns remain. Thresholds matter, rates matter, feedbacks matter. These rules govern every extinction regardless of cause. Chapter 15 is not meant to inspire despair. It is meant to replace illusion with understanding. And extinction is not punishment or failure. It is the planet responding to imbalance. The tragedy of mass extinction lies not in the end of life, but in the loss of unique histories. Each species erased represents millions of years of evolutionary experimentation that will never occur again. This is why extinctions matter, even if life recovers. Recovery does not restore what was lost. It builds something new from fragments. The 5 mass extinctions are therefore chapters of loss and creation intertwined. They mark endings that enable beginnings, but always at a cost. As we approach the final chapters of this series, the focus shifts from explanation to reflection. What does it mean to be a species capable of reading this history while potentially repeating it? Earth does not need saving. It will continue long after any single species disappears. What is at stake is the continuity, of complex life and the world that supports it. Deep time offers clarity. Dominance fades, resilience matters, and speed determines survival. The story of mass extinction is ultimately the story of limits. In the final chapters, we will confront those limits directly and ask what role, if any, humanity chooses to play within them. Standing at the edge of deep time forces a shift in perspective. When the history of life is compressed into a single narrative, humanity occupies only the final seconds. Yet, within those seconds, a species emerged capable of altering planetary systems that once took millions of years to change. Chapter 16 examines what it means to live at that edge and what the record of mass extinctions implies for responsibility, choice, and consequence. Mass extinctions teach that Earth does not respond to intention. It responds to physics, chemistry, and biology. The planet does not recognize good or bad actors, only inputs and outputs. Energy added to the system produces warming. Carbon released accumulates. Habitats removed reduce biodiversity. These are not moral judgments. They are outcomes. This distinction matters because it removes comfort. There is no negotiation with feedback loops. Awareness alone does not weaken them. Only changes in physical processes do. Past extinctions show that warning signs are always present. Rising extinction rates, chemical anomalies, and ecological stress appear long before collapse becomes obvious. Societies living through those early phases may not perceive crisis because daily life continues. Ecosystems do not fail everywhere at once. They unravel unevenly. This unevenness creates denial. While some regions experience severe stress, others appear stable. This pattern delays collective response until thresholds are crossed. By then, momentum dominates. Humans are not the first dominant species to expand rapidly. Reef builders once transformed oceans. Land plants reshaped the atmosphere. Dinosaurs altered terrestrial ecosystems through sheer biomass. None intended harm. None foresaw collapse. Dominance itself creates blind spots. What distinguishes humans is scale, speed, and connectivity. Global trade links ecosystems that were once isolated. A change in one region propagates quickly to others. Disturbances are no longer local. They are planetary. This connectivity amplifies both vulnerability and potential response. Harm spreads faster, but so can mitigation. The same networks that distribute stress can distribute solutions. The fossil record shows that survival during extinction favors certain traits. Flexibility, small size, generalist diets, and refuge access increase odds. Intelligence can function as a meta-trait, enabling rapid behavioral adaptation without genetic change. This gives humans a theoretical advantage. However, intelligence also increases extraction efficiency. It magnifies impact. Whether it functions as a survival trait depends on how it is applied. The core challenge is time. Geological feedbacks operate on timescales that do not align with political or economic cycles. Decisions delayed by decades can lock in outcomes for centuries. Once ice sheets destabilize or carbon reservoirs release, control is lost. Past extinctions show that once tipping points are crossed, collapse accelerates regardless of subsequent restraint. Prevention must occur before those points, not after. This creates a paradox. The cost of action is highest when the threat feels abstract. The cost of inaction becomes absolute when the threat is undeniable. Deep time favors early restraint, but short-term systems reward delay. The fossil record does not show any species successfully reversing a planetary-scale extinction once it began. Recovery always followed collapse, not prevention. This does not mean prevention is impossible, only that it has never been attempted at this scale. Human societies have altered trajectories locally. Rivers have been restored, forests regrown, species reintroduced. These successes demonstrate capacity, but they remain limited in scope relative to global trends. Chapter 16 does not argue inevitability. It argues constraint. The window for effective action narrows as feedbacks strengthen. Choices exist, but they are bounded. There is also a misconception that avoiding extinction requires perfection. The record suggests otherwise. Life can tolerate stress within ranges. Reducing speed and magnitude of change may be enough to avoid cascading collapse. This reframes responsibility. The goal is not to freeze the planet in its current state, but to keep Earth systems within adaptive limits. Stability in deep time is not static. It is bounded variability. Another lesson from past extinctions is the importance of refuges. Protecting diverse habitats across latitudes, depths, and climates increases survival odds. Redundancy matters. Fragmented, isolated reserves are insufficient. Connectivity allows migration and adaptation. This has practical implications. Conservation is not about preserving icons alone. It is about maintaining functional networks that buffer change. Mass extinctions also reveal that recovery creates winners and losers unpredictably. No species can guarantee its future dominance. Humility is therefore rational. Planning for resilience rather than supremacy aligns with deep-time reality. Human culture often frames survival as competition. Earth history suggests cooperation with planetary limits is more effective. Species that overshoot vanish. Those that fit persist. This perspective challenges narratives of control. Technology does not grant exemption from physical law. It can alter pathways, but not abolish limits. Geoengineering, for example, may reduce warming, but carries risks that could trigger new feedbacks. Interventions must be evaluated against deep-time consequences, not short-term gain. Chapter 16 emphasizes that meaning is not provided by the planet. Earth is indifferent. Meaning is constructed by species capable of reflection. This places responsibility squarely on humans, not as rulers, but as participants. The 5 mass extinctions did not ask whether life deserved to survive. They happened because systems changed. The current trajectory will resolve similarly, unless altered. There is also a deeper implication. Intelligence emerged from billions of years of evolution shaped by extinctions. If intelligence cannot coexist with planetary limits, it may be a transient experiment. If it can, it represents a new evolutionary pathway where behavior substitutes for biology. This would be unprecedented, not in power, but in restraint. Deep time offers no guarantees, but it offers clarity. Every dominant species believed its era would last. None did. Permanence is an illusion created by short lifespans. The question then is not whether humans can save Earth. Earth does not require saving. The question is whether humans can save a version of the world that supports complex life, including themselves. Chapter 16 concludes with a recognition. The 5 mass extinctions are not warnings sent to humanity. They are records of what happens when limits are crossed. They define the rules. Knowing the rules does not ensure compliance, but ignorance is no longer an excuse. The final chapter will step back completely, not to predict outcomes, but to place this moment within the longest possible frame. From that distance, the meaning of mass extinction becomes clearest, not as catastrophe alone, but as a measure of how life interacts with the planet that creates it. What happens next will not be judged by history. It will be written into it. From the farthest possible distance, Earth's history compresses into a single rhythm. Creation, expansion, collapse, renewal. This rhythm is not emotional or moral. It is mechanical. Energy flows through the planet. Matter cycles, and life emerges where conditions allow. Mass extinctions are not interruptions to this rhythm. They are part of it. Chapter 17 steps fully outside the present moment. It looks at Earth not as a home or a responsibility, but as a system that has been running for over 4 billion years. From that scale, the 5 mass extinctions are neither anomalies nor endpoints. They are recalibrations. Life appeared quickly once conditions allowed. It spread relentlessly, adapting to every niche. It altered the atmosphere, oceans, and land. In doing so, it created the conditions for its own crises. This pattern repeated again and again. Success led to instability, instability led to collapse, collapse led to reinvention. There is no evidence in the geological record that Earth prefers complexity. Complex life appears when conditions permit and disappears when they do not. The planet does not trend toward intelligence, biodiversity, or stability. It trends toward balance between energy input and dissipation. Mass extinctions occur when that balance is disrupted too quickly. Ice ages, volcanism impacts, and biological feedbacks all shift energy flows beyond what ecosystems can absorb. Collapse follows not as punishment, but as correction. This framing changes how extinction is understood. Extinction is not failure of life. It is the system shedding excess complexity when conditions no longer support it. The biosphere simplifies until it fits again. From this perspective, recovery is not redemption. It is adjustment. New forms emerge not to restore what was lost, but to occupy what remains possible. The 5 mass extinctions therefore mark transitions between different versions of Earth, different climates, different dominant life forms, different atmospheric compositions. None of these versions is final. Humans exist within one such version. A warm, interglacial world with high oxygen, stable coastlines, and abundant biodiversity. This configuration is not permanent. It never was. What makes this moment distinct is awareness. For the first time, a species can read the record written in stone and understand the consequences of crossing planetary thresholds. This awareness does not grant control, but it does grant context. Context removes illusion. It shows that the current world is not guaranteed. It also shows that collapse does not require malice or intent, it requires imbalance. The deep time record is indifferent to narratives of progress. It does not show steady improvement. It shows fluctuation, long, stable intervals punctuated by rapid change. From that view, the modern era is not special. It is simply fast. Speed is the defining variable. When change occurs slowly, ecosystems adapt. When it accelerates, they fracture. This rule holds regardless of cause. Ice, volcanic gases, asteroids, or industrial emissions all produce the same outcome if rates exceed tolerance. This is the core lesson of mass extinction. Not that life is fragile, but that it has limits. Resilience exists within bounds. Chapter 17 is therefore not a warning and not a conclusion. It is a lens. Through it, the past, present and future align into a single system. If humanity stabilizes its impact, Earth will continue changing, but within ranges that support complex life. Future geologists will see this interval as a disturbance, not a boundary. Biodiversity will decline, then recover without full collapse. If stabilization fails, this moment will appear as another sharp line in the rock record. A sudden loss of species, chemical anomalies, and a long recovery interval will define it clearly. Future life will inherit a different planet shaped by this collapse. Either outcome fits within Earth's history. The planet does not require a particular result. It has persisted through far worse. What is at stake is not Earth's survival, but continuity. Whether complex ecosystems and technological civilization coexist long-term, or whether one gives way to a simpler biosphere. Mass extinctions show that continuity is rare, complexity is costly. Maintaining it requires conditions that do not arise automatically. This leads to a final reframing. Responsibility is not about saving Earth. It is about deciding whether to remain compatible with it. Compatibility does not mean stasis. It means operating within feedback limits, slowing change, allowing adaptation, preserving redundancy, and accepting constraint. Deep time does not promise success. It only defines consequences. There is also humility in this view. Even if humans vanish, life will continue. The planet will not remember civilizations, but it will record their impact. Stone does not care about intention, only effect. This realization strips away both arrogance and despair. Humans are neither masters of the planet nor insignificant. They are a geological force with a choice of how that force resolves. The 5 mass extinctions did not ask permission. They followed physics. The 6th, if it fully manifests, will do the same. Chapter 17 closes the narrative where it began, with a planet in motion. Nothing is fixed. Nothing is owed permanence. Life persists by fitting within change, not by resisting it. The mass extinctions are not stories of the past. They are the operating manual of the planet. Whether that manual is read or ignored does not alter its rules. It only determines who remains when the next chapter is written.